Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're excited to have Hee Wang today. He's a PhD student at UIUC, works with Romit Roy Chowdhury, who is quite familiar to many in MSR. He himself is no stranger to MSR. He's interned here twice. Today he'll be talking about his work on multimodal sensing, gesture recognition, and indoor localization.
Thank you. Yeah. Good morning. It's my pleasure to be here to talk about my research work, which is on using mobile devices to sense a user's location. And let me start by saying a few words about the background of this research. In a matter of 10 years, from 2005 to 2015, the mobile phone has transformed from a basic communication device to a smart device that performs sensing, computing, and communications. And today's smartphone has 14 sensors on them, more than 5 communication interfaces, and even more CPU power than the Apollo guidance computer that landed man on Moon. Right? And given these devices are always on and always with us, we envision these devices as a general-purpose human sensor, capable of zooming into our lives, understanding our daily activities, preferences, and behavior patterns. And the Silicon Valley has been calling this the quantified self. So essentially suggesting that the data from these devices can be used for core inferences about ourselves, and ultimately enabling a wide variety of applications. So a few applications are already on the market. Let me just talk about a few examples. Using the accelerometer data on the smartphone, it is possible to count the number of steps that a user has walked. And many calorie score applications have emerged. And the newer smartphone has the skin conduction sensor that can measure the heart rate and enables many mobile health applications. And of course, GPS gives us the driving direction, right? Well, these were really cool and important a few years back, but now they seem obvious. And user expectation for the next generation of mobile application is much higher. And if we want to deliver better applications for the future, research is necessary towards robust, efficient, and practical inferencing techniques on humans. And here are just a few examples that are still quite hard today. Finding a user's indoor location, right, estimating the posture of a person, and tracking precise hand gestures, and various forms of context awareness. So my research focuses on developing inferencing techniques using the multimodal sensor data for mobile devices, such as smartphones and smartwatches. And I believe these inferences can enable new kinds of human-centric mobile applications. For example, consider business analytics. Right? So if we understand this user's location, postures, and gestures, then we can understand the user's shopping behavior in a grocery store. And interestingly, this is already happening extensively in the web. Our clicking patterns or mouse movements are all driving a billion-dollar business called web analytics. And I believe our footsteps in the indoor environment is indeed like the clicking streams online, right? And when we look at a cereal box in a grocery store, it is indeed like right-clicking an online item. So this physical and vibe analytics are really similar, but still this physical analytics is still not present today, simply because we don't have the ability to understand the user's location, postures, and gestures. Now, suppose we have this location, posture, and gesture inferences building blocks, then I believe we can enable this physical business analytics. And many other applications open up. For example, understanding the location and orientation of the phone can enable augmented reality for indoor museum, right? And sure.
Your previous thing on business analytics, do you also consider using the infrastructure like cameras and things, which might be a more direct indicator of where you are?
That's a possible solution, right? So if you run the analytics using a camera, then that's not a possible solution. Yeah, but there will be other challenges such as like conclusion, something else, right? So there are different trade-offs. Yeah. So an gesture-based control can be done by just wearing a smartwatch. And finally, this virtual gaming, virtual reality around the corner, and they are emerging. And this understanding the postures and gestures of users' hand can be key building blocks for such immersive gaming experiences, right? And if you look at these building blocks, across different models, the common denominator is really the location, right? The location of the human body in indoor localization, and the location of the arm in pose estimation, and the location of the hand and fingers for precise hand gestures. So my talk is really about how we can leverage smart device sensors to do this macro to micro localization on the human body. So let me start by talking about indoor localization. So the question about indoor localization is essentially, where am I in the indoor environment? And there has been a huge amount of work on this topic. Let me just quickly sample the key ideas. So the first question is, why not we just use outdoor localization technology, for example, GPS? Well, the problem with GPS is that the GPS signal do not penetrate well into the buildings. And even some that do, that bounces too much in the indoor environment, that leaving the GPS receiver a poor accuracy if at all. And Wi-Fi turned out to be a reasonable alternative, right? Especially given its wide availability. And it's probably the most popular approach thus far. Let's assume we have a couple of Wi-Fi points in the environment, and now when the phones run a Wi-Fi scan, they can get a list of Wi-Fi signals. Right? As the user walk around, the received signal strength will change. So therefore, the signal can infer the user's location. But to make this happen, somebody has to go to everywhere and then build this mapping between the signal strengths and the user's location. That takes a lot of effort. And even worse, this mapping changes over time. So therefore, to ensure a high accuracy, we need to periodically calibrate the signal and build this map. Right? And Wi-Fi is not the only approach that people have considered. We also look at deploying beacons. For example, Bluetooth beacon and sound beacons. Right? For the sound beacon case, so people deploy a couple of sound beacons in the environment, and then we can use smartphone microphone to calculate using timing to calculate the distance between the phone and the beacon receiver, right? And from that, they can triangulate and figure out the user's location. And Bluetooth beacon is another approach that has a smaller range, and then when the user passes by, the phone can hear the whisper of the Bluetooth beacon, and then can figure out the location of the phone, right? But the problem with this beacon-based approach is that the huge deployment and installation cost, right? So therefore, many companies like Google, Cisco, Intel, Samsung, they insisted on us to provide a system that is software-based and scalable. So under this context, we started thinking, can we build something that do not rely on the infrastructure? So that seems possible. And also around the same time that the smartphone has this motion sensors, accelerometer, compass, and gyroscope. So we started thinking, can we use this motion sensor themselves to figure out the user's location, as opposed to relying on a Wi-Fi or acoustic signal from the environment. Right? So that seemed possible because when we use the accelerometer data, well, when the user walks, the phone bounces, right? That should tell us the steps that the user has walked if you just use simple filtering techniques. And also the compass will give us the direction, in which the user is walking, right? So if we combine the direction and distance, we can estimate this actual path that a user has walked. So we tried this, we collect some data, and then it turned out we failed miserably. Because, so then we come back to literature and we found this method called dead reckoning. And dead reckoning is essentially fundamentally difficult because our environment has these mitals all around, and these mitals cause the compass data to fluctuate. And when user play with the phone also bounces, right? Therefore, all these together, arrows add together, that makes this direction tracking deviate from actual path over time, right? But actually, in the past, when people did not have GPS, that reckoning has always been used for ships and planes to figure out their location. For example, in 1922, Charles Lindbergh has landed in Paris after a non-stop flight from New York. And that time there was no GPS. And Charles Lindbergh just used that reckoning. And how could he do that? It's such a long trip and he just used the reckoning. The trick was that he obtained fixes from the stars and used that to guide themselves. Right? So once we knew this, we started thinking, hey, can we magically bring some landmarks or stars to the indoor environment? Once we have this, when a user walks, the moment he hit a landmark, we can recite the user's location and the user can direct it from there. And we can keep doing the same. So therefore, over the time, this new estimated path in this green line is much closer to the actual path. That would be awesome. But the problem is that in indoor environment, we don't have the stars or landmarks, right? So we start looking into our environment and start thinking, can we find some landmarks? And at first, we cannot find any. But then when we collect some data and then go back to life, and then we suddenly realize that if we see through the data, through the eyes of the sensors, right, then we can find many unique patterns in the environment. For example, we find this unique magnetic fluctuation, and that could be potentially used as a landmark. And out of curiosity, we also check where does this happen. It turned out this happened near a water fountain. And we also observe other patterns such as accelerometer data. So we find some overweight and lost weight in the accelerometer data. And by the way, our smartphone today has the barometer data that can measure the pressure changes. So we also observe these pressure changes along with this accelerometer pattern. So it turned out these patterns are caused by the elevator. And at this particular spot, right, when the user passes by this, the cellular signal drops significantly and then again comes back. So it can also be used as a landmark. And there are many other examples such as Wi-Fi fluctuation, turning around a corner, taking stairs, and so on and so forth. So we can use them as landmarks to help us calibrate the user's location. But of course, we cannot predefine all these patterns because we want our system to work all over the world, in all the buildings. We don't know whether their buildings have this water fountain or have the elevators. So the idea is to automatically learn this pattern from the environment. Yeah. So using this core idea, we developed a system called Unlock, unsupervised indoor localization. And we need to solve three main design questions. One, how to automatically detect landmark. And second, how to localize the landmarks. Right? And third, how to localize the users. And our solution to all these problems are interdependent and recursive, but let me try to explain them one by one. So let me start by talking about how to automatically detect the landmarks. So let's say, consider a user walking in this building, and let's say just for the next 5 minutes that we have a reasonable estimate of user's location. Say, perhaps from that reckoning, but this is a rough estimate. But we will soon relax this assumption and explain, even that reckoning is bad, how we can bootstrap our system. Let's say we have a basic estimate, and then at the same time, we can collect the sensor data from the user. So therefore, we will have a location to sensor tuple. As more and more people walk in this environment, we will have more and more such tuples, right? And then we can extract features from the sensor data, and then we can get this location to feature tuple, right? Because we are interested in the unique sensor pattern in the feature domain, so we run an unsupervised clustering algorithm on that. So this is just an illustration, but in the system we have multiple features, so it's a higher dimension. But the idea is that the same pattern here in the same cluster will share the same feature pattern. But that's not enough because we want to know where does this pattern really happen in the real world. But we can do that because we already have this crude location estimate. So we can map this pattern back to the floor plan. Let's see one example. Let's say this right points. So it turns out these right points also happen in a small cluster in a geographic space, right? So which gives us a sense that it can be used as a landmark. But not everything is as good as this. For example, if you look at these blue patterns, it happens in multiple locations. So the way to deal with that is that we can leverage the Wi-Fi signal. But this is different from Wi-Fi-based indoor localization. You don't need to manually label the location and Wi-Fi mapping. As long as you know the Wi-Fi signal of these two clusters are different, that's enough to distinguish them. So even if you use Wi-Fi, it still comes for free. Right? And some pattern like this green one, it just happens everywhere. So it turned out this pattern is because when the user is walking, it also creates a unique pattern. But walking just happens everywhere, so that's not helpful at all. So just because it's a sensor domain cluster, not necessarily mean it's a landmark. And because we have this feature, we can, sure.
I have a question for you. So does this work best in sort of narrowly constrained hallway type of environments? What about like a mall where the hall is much, much larger than some of the examples that you've shown?
Yes. So the system will work better in a narrow corridor or not open space. But the system still can work in those scenarios, but with a little bit worse accuracy.
And does it get impacted by, out of the things that you've shown, it doesn't seem to get impacted by more people in the mall, for example?
Oh yeah, it's not impacted by that. Because when more people walk around, the Wi-Fi signal could fluctuate a little bit, right? But this magnetic signal is quite stable still, and the initial pattern of the user's walking path.
Environments did you test on?
We test our system we also test our system in the engineering building, office building of different places, and we also test our system in the shopping mall. Yeah. And yeah, so if we try to play with these features, we can generate different kind of landmark. In our system, we use this inertial landmark, meaning we use the gyroscope and accelerometer data. We also have the magnetic landmark and Wi-Fi landmarks. So because our environment has so many sensing data, and they are unlikely to be evenly distributed. So, and also we can always use this Wi-Fi signal to divide our area into subzones, right? So our assumption, our hypothesis is that our indoor environment have enough landmarks for us for localization. So that just means we have found the stars in our indoor environment, and we can use this for periodically calibrate the user's location and then provide high accuracy. Sure.
Maybe I missed this. Part of the assumption also that at the landmarks, the set of sensor signals that you see don't change over time or invariant?
Yeah, so the signal in the short time scale, it doesn't change, but in the longer time, it does change over time. So what we do is that after a period, we regenerate the landmark such that the signal can be tuned, right, to the state of the latest environment. That is possible because we have this data is automatically generated, right? So there's no manual effort to go there, label again and again. So potentially what we can do is at the end of the day, you regenerate, and that should be work for at least 1 day.
So what's an example of when it changes in the long term but not in the short term? Can you give an intuition for why it is?
For example, the Wi-Fi signal, I think it should work for at least 1 or 2 days. And magnetic signal that works even longer. I think it works for more than 1 or 2 months.
That would be like if someone has installed a new drinking fountain or something like that.
Yeah.
The magnetic signatures would change.
Right. So in those cases, the building structure changes, then that could change. But typically, it's quite stable.
So this is the relative coordinate system of the landmarks. So what's the coordinate system here?
Yeah. So we need to manually label 2 places to figure out the absolute location.
So manually do what? So you go to. So you walk around the place manually. Is that so? How do you bootstrap? How do you
Yeah, so I will talk about how to bootstrap in a minute, but we need to manually label where is the building entrance and one of the like stairs or elevators. But you don't need to go there. Let's say I can stand here and label what is the building entrance of building 42.
The assumption is you have the map.
The assumption, the thing is that we don't need a detailed map how label where is the walls. We just need to have, you just need to tell me what two information. Where's the entrance? Where is one of the elevators? That's our requirement.
Sure. Maybe you'll get to it later. I don't know. Are there any applications to a home environment?
Yeah, I think there will be applications for the home requirement. For example, if you leave one room, you want to automatically turn off the lights, or you want to track the aged people alone at home, how things going on. I think there will be many applications.
I was thinking there'd be fewer Wi-Fi signals, most likely.
Yeah. I think for home environment, fewer Wi-Fi, but we still can rely on the sensors to track your steps. Yeah, sure.
Just curious, so what if many people are using Wi-Fi hotspot, and they're moving, so will it impact this accuracy?
What if multiple people are using the hotspot and they are moving? So then under this scenario, what is the accuracy? Right. So in our system, because we can rely on this, step counting and tracking, and we also rely on magnetic inertial patterns. So we don't rely heavily on the Wi-Fi. So that means we only use the most stable Wi-Fi signal. We can afford that because we rely on other stuff. So we only use highly selective Wi-Fi signal, use the cruise features. So that increased the accuracy for those networks. Yeah. So, but that sounds good. But wait, right? So we assume that we have a reasonably good data reckoning. But what if that reckoning system is not that good, which may be always the case in the real world, right? So what happens then? So our idea is that let's say the user walk past three sensor patterns like this, red, blue, and green, and different user will walk the same path, but just because of the tracking error, this path is going to diverge from each other over time. But the initial point shouldn't be too bad. It's reasonably good for the initial point, that reckoning, right? So we can use those traces to figure out that this right pattern actually happened in a small area. They should be recognized as a landmark. And then we use the centroid of the landmark as the estimate. But this is just the initial estimate. It's not accurate at all. This is not perfect at all, but it's a reasonable estimate. And then because these errors from different devices, different hardware and different phone, different user step size counting, they are uncorrelated. So if you pull out the real world data, and this is one example, right? This right square is the true landmark location, and each of these blue points shows the estimated estimation from the data reckoning path. So as we can see here, they are really uncorrelated because of the hardware noises and the human step size and out patterns, right? So their centroid can be used as an initial estimate. And from that, but the problem here is that this blue and green patterns cannot be recognized as landmark because they are scattered in a quite large area. We are not sure what really happened, right? So what we can do is, since we know the first one is a landmark, we can recite user's location to the first one, and then that reckoning from there. And now the second one, is blue one, becomes happening in a reasonably small area, right? And then we can recognize it as a landmark. Then we can keep doing the same, and then finally recognize that the last one is also a landmark. So in other words, we can gradually grow the landmark from the region of the building, and then finally fill the whole building in the bootstrapping phase. But these estimates are not perfect. They have errors. But the good news is that we always have users walk in our building. So we can leverage these new user traces and fit new user traces to our system and to improve the estimate of landmark location. So here's how we do that. Let's say the user walk in the building, and then we can we can always find whether there's a new landmark, and we can also find its existing landmark. And then we can update the landmark list, right? And then when more users walk in the building, the landmark location estimation will become better, and which in turn will improve the user location error, because the user rely on the landmark to recite themselves, right? If you have a better landmark, you have better user estimation. As more and more users walk in and then we have new data from for our system, this landmark location error and user location error both decrease over the time. And we demonstrate so we test our system in more than 6 buildings, including shopping mall, university, and office buildings. And we test our system in using 5 different Android models with more than 20 users. And currently it's running live in our lab, CSL. And even though we use the landmark generated half years ago, it still can work robustly. And to get a quantitative evaluation of the system, we collect the ground truths from the shopping mall, ECE, and the CS buildings. And this graph shows the result. Yeah. And the x-axis shows the error in meters, and the y-axis shows the CDF. And different lines shows the system performance over time. And different lines shows the system performance over time, and we can see that the system performance improves. And after around 2 hours walking, we can achieve a median accuracy of 1.63 meters. So in summary, right? So our nature has diversity that guided Charles Lindbergh to find his way to Paris. And then our indoor man-made nature, our indoor environment, also have the diversity that can be used to find landmarks and then help us improve our indoor localization system accuracy. And Unlock achieve a median accuracy of 1.63 meters with no infrastructure cost and no manual calibration. Sure.
So back to the question I asked earlier, your summary numbers kind of averaged over all the places that you tested, right?
Yeah.
So in a place like this, what would you expect? In a place like that mall?
In a place like this, I think the accuracy will be worse than the corridor scenario. We don't have an exact number for that right now. Yeah. So we test our system after publishing the paper. We continue working on this work for another 1 year and optimize different things. And we deploy our system in different buildings. And here's one example: the users using our system, and what KDC on the phone screen is showing on the left part of the video. And when a user passes by room 246, and Unlock system can precisely capture this. And we also have a backend server that can automatically calculate all the landmarks from different users for the building and collect data from different users and generate landmarks, and also visualize the traces and do all the localization management. And we demonstrate our work to different companies at different places. And TKE is an elevator company who are interested in our system because they want to use our system for their elevator scheduling. They have the elevator in Wall Street, again, at a super tall building, and people are tired of it, waiting there for the elevator for a long time, right? They want to use indoor localization to schedule their elevator. And during these demos, we assume that the phone is in user's hand, and the user is looking at a screen and walk like this. But in our demo to Intel, they tried our system at different places. They tried to put a phone in the pant pocket, in the shirt pocket, and all kinds of places and orientation. And the system just failed in those cases. And this reminded us that indoor localization is not just about navigation. You cannot always assume the phone is in user's hand and you look at this and then do all this tracking. So the question is how we can still estimate a user's walking direction, even if the phone is in user's pocket and other different places and different orientation, right? So we solved this challenge with another Mobius paper, but because of time interest, I cannot go into details, but I will just show a very brief demo of that. So in this video, the green line shows the estimated walking direction from the user. And then while the user is walking, the user try to hack the system, and they're trying to change the orientation of the phone, and we still can estimate the faults on the phone and then quickly analyze the user's walking direction. So, and then we integrate the system and unlock together, and then Samsung purchased a research license of our work, and they are interested in pushing this to their Android platforms. So with that, I will move to the next part. But before that, any questions?
Yeah, your results actually got me thinking. You said your accuracy was 1.63 meters?
Yeah, in a meeting case.
Yeah, so again, I'm not totally familiar with the space, but I do see recent work on this, on indoor localization using Wi-Fi that talk about decimeter level. Decimeter, 1/10 of a meter.
Yeah.
How does your thing compare?
So yeah, I'm aware that many systems can achieve better accuracy, right? But typically they will require like deploying infrastructure, deploying hardware, or you need to wall drive the detailed Wi-Fi information such that it can provide that accuracy.
It requires the extra piece of hardware. So, I mean, this has been known for like ages that if you can take one approach, which is that you apply infrastructure and hardware, which you can get centimeter level accuracy. In fact, you can hear both these now here, but Bodhi deployed a cricket system long time back, which would get centimeters, but it was ultrasound and you did stuff in the AP. And so the other one with Kyle and Sachin and all these guys.
Yeah, this was Sachin.
Yeah, they're applying extra piece of hardware. The access points.
Yeah. So in those cases, it may not scale to all the buildings easily. Yeah.
What's the weakness of the system? I actually missed. I'm so sorry. I thought it was 10:30. I don't know.
Yeah.
Exactly at 10:31. Anyway, what is the weakness of the system?
Yeah.
In your
So
opinion?
yeah, the weakness, I think, our system is still in some sense rely on the direct reckoning, rely on the step counting and the direction estimation, right? So even though we kind of solve the problem, even if we change the orientation, put it in different places, but the user behavior, they could be not as our expectation, right? They can just check the phone like this, like I'm talking, right? And then the system may think you're walking. So, I mean, in some cases, we can still rely on some Wi-Fi as the lower bound, but in those cases, the system needs to handle carefully. User behavior may not always expect it.
Have you tried, well, what would be the challenges in doing it passively? Like, so you said that it might be in your pocket or something like that, but if the user is just, they're not really trying to locate right now, they've been walking around in the mall for 10 minutes, they can't find their store, now they want to start localizing. And so you'd have to keep all these sensors on, for example, on a passive, so people might not like the battery drain.
So in those cases, yeah, we keep the sensor on. The tracking is not really a problem because it's relatively in a stable place, even if it's in the pocket, right? But what about energy? We don't have an energy number, but I think this continuous sensing is quite popular, and I know many of you are working on continuous sensing projects. And newer smartphones have the additional hardware that can, additional CPU, lightweight CPU that can precise this easy task such as sampling and do some simple calculation. So using that will reduce your energy cost. Yeah. So yeah, let me move to this post estimation problem. So here, what we want to do is we want to understand the pose of the user, and this is working this year's mobile basis. So can we track the arm posture using just the smartwatches, right? And so by posture, I mean the 3D location of wrist and elbow. And there are a couple of challenges. First of all, there are noises in the sensors. So accelerometer gyroscope, right, is not perfect. And over time, these errors will accumulate. So you cannot just use double integration. And also, this accelerometer data is only on user's wrist because smartwatch is on the wrist. So how can you infer the elbow location, right? You don't have, it seems we don't have enough data. And then the third one is that we don't have training data. We don't want to train the user on a specific side of gestures such that we can work for those gestures. We want to do free-form gestures. So those are the challenges we are facing. But this arm posture tracking problem is not new at all, and many researchers have looked at this. For example, from the robotics or biology domain, signal processing domain, people have been looking at these problems. And the most closest work to us is one work that also trying to use the smartwatch to figure out users' pose. So what they do, they leverage a couple of opportunities. First of all, our elbow is always going to be on a circle around by our shoulder, right? And then the wrist is on another circle surrounded by our elbow, right? So based on these two constraints, we can actually narrow down the search space quite a lot. And then people also borrow the medical domain information because our arm have 5 freedom angle of freedom, right? And then each of them has a range of constraint. For example, in this theta 4 here, our arm can only move from 0 to 150. We cannot move in a negative way, right? So if we combine these constraints and together, we can narrow down the search space. But that's still not enough. So that's why they also train a preset of 15 gestures, and then they can do a pretty good job there. Right? But what we want to do is we want only use the smartwatch, but we also want to do the freeform gestures. So there are a couple of opportunities we are going to leverage. First of all, once we know the orientation of the watch, that can be very, very valuable to us. That can infer the user's wrist and elbow location. And second of all, if you use the acceleration from the watch, that can show some information about a user's movement. If we combine that with like hidden mark model, then probably we can get a better estimation, right? And of course, we can also leverage data structure to improve the speed of our tracking system. So let me first explain what do I mean by watch orientation. By watch orientation, I mean the 3-axis pointing direction of the smartwatch. And now we found that so for a given orientation, basically we iterate all the angles possible, and then from that we can find a subset of combination that satisfy this particular orientation. With this subset theta, we can map this theta to the possible location of users' wrist and elbow. Sure.
Just to clarify, you said 5 degrees of freedom. 3 here, 2 here, right?
Yeah.
What is this? Isn't this another one?
Yeah. Oh, sorry. There are things.
Wrist rotation.
So here I think we have we.
Yeah, your picture slides back.
Yeah. Let's see. Yeah. So here we have 3. 1, 2, 3, and there's one here actually.
So this.
So that's one come to here. So when you do this, it comes to the upper part. So count it there. Yeah. Yeah. So and then so basically from these 5 angles, we can try all the combination and see which one satisfies this orientation constraint. And from that, we can map back to the point cloud and see, okay, these are the possible locations that satisfy this orientation constraint. So, and our key observation is that suppose we know the 3D orientation of the watch, the possible wrist and the elbow location are quite limited. For example, right, in this case, when our orientation is like this, the possible wrist and elbow will be like this, right? So as showing this green and the red dots. And it's quite limited. So let's try to quantify that and see how good is this opportunity, right? So we can easily do this because we can always try different combinations and see how it goes, right? The metric we have is the area of the point cloud, right? Here, and divide by the whole sphere area and see what is the ratio. If the ratio is low, then that's good news to us. And we plot this CDF. X-axis shows the ratio, X-axis shows the ratio, and Y-axis shows the CDF. And we found that median case, we typically have 9% of the sphere. So that means it's a reasonably small area, right? If you just use the centroid, probably you can do a reasonably good job. But what if, how do we know that, how can we figure out the user's movement within this constraint, within this narrowed down area, right? So the idea, sure.
Your median is fine, but can you just go back to the graph for a second?
Yeah.
But your 88 or 98% is really bad, right? I mean, it's 30%, 40%, like it could be anywhere in that sphere.
Right. So yes, in many cases, it's not that good, and that's true. And I will just explain how we can improve this. Yeah. So the opportunity is using the accelerometer data, and from that we can get an inference of the user's wrist movement. Let's say one example, right? When the user is like punching, like this, so the orientation of the watch doesn't change at all, right? But your elbow going to move backward and forth, right? And so the tracking, the naive method will think you don't move. It's a static point. But since we know the acceleration of the watch, so we should do better than just give a static estimation. So that's the intuition. So how we can leverage accelerometer data here. So the question is to understand the real sequence, right? From that sequence, this is like a location A and B and C. From that, we can actually infer the acceleration. And we also have the real-world acceleration from the user's watch. And from this trace, for any given trace, right, we can, from the two locations, we can infer velocity. From two velocity, we can infer acceleration. So basically, the question is how we can combine this inferred acceleration from the smartwatch with what the acceleration that trees give us. And then we combine this together and consider the noise model and then figure out what is the best possible estimate. So then the thing is here, what we can do easily is that we can use a third order Hadamard model, right? So we can combine three states together, and then if you consider three states, and then you can track the acceleration, and from that you can combine this together to build the arm traces, right? But the problem is that this is slow, and this third order Hadamard model cannot be solved efficiently. So we need to reorganize these things to make that efficient algorithm can apply. So if we combine these three locations into one state here, then we can use, that becomes a first order Hadamard model. Then we can use a VDB decoding algorithm, which is efficient for decoding first order Hadamard model. So the idea is to build three adjacent locations to one state, and then because two adjacent locations will tell you the velocity, and then from that, actually each state itself will embed this acceleration information. And we also have this acceleration measurement from the watch, right? So we can combine this together and also take this noise model into consideration. From that, we can infer the trace. We also consider the continuity because your trace is going to be smooth, right? So this overlapping should be the same. And we also consider the point cloud limitation. Given this orientation limitation at this particular time, your possible candidates will be in their range.
So you're saying that you're doing this so that you can use Viterbi?
Yeah.
But Viterbi is order n squared in the number of states. And
exactly.
There's a state explosion. It's like you're combinatorially increasing the number of states over which you're doing the Viterbi. How does that?
Right.
So why does this benefit in terms of speed up?
Right. So I think what you are saying is exactly right because.
The usual way in which you speed up something like this is to not do Viterbi, but to do some kind of beam search. So you don't actually look at all the Viterbi paths.
And why would you use? You're not using multiple states here, right? I mean, you have a first order.
Yes.
HMM, right?
So right. So previously, if you consider three states separately, then that would be third order. So we merge them together to use VDB. If you have three states, probably you have to brute forcefully search that in exponential time. Now at least we can do it in polynomial time. But
are you actually doing full Viterbi over all the states?
But I will try to reduce that in the next slides. Like you said, let's say we have n possible locations, right? And then the t time steps. Then our state number will be nq, right? And then the running time will be n to the power 6, right? And n will be a huge number, like thousands possible locations on the sphere. So that's not quite acceptable in how we can reduce the number of states. So we try to reduce the number of states by actually only looking at two adjacent locations. From the two locations, actually now for each state, you can encode the velocity, not acceleration though, but we can always build this acceleration transition into the state transition. So now from one state to another state, this transition it shows the acceleration, right? Now you can move this acceleration from the observation to the transition. Now at this point you can, advance and then advance forward. Then we can have, of course, we also have this continuity and this orientation constraint, but we can reduce the state number to n to the power of 2, and now we can do n to the power of 4 multiplied by t, and we can even do better. So because we have this continuity constraint, because like this state has to be smooth, right? So that means in a weight-B decoding, each stage, many of them will be 0. And so if we can reorganize this such that they happen in a continuous chunk, and then we label the start and end points, then we can further reduce the O(n) complexity. So then we can get something like O(n) to the power of 3 multiplied by t.
When people try to do large-scale HMM tracking, you don't try to run Viterbi, right? You run some kind of a beam search. You just run the most promising K paths, something like that. I mean, I don't know if you're aware. So even n-cube seems large, and so you're running an n-cube algorithm on a large n on a phone. Is that what's happening?
So
So you're running this on a phone?
No, not on the phone. We run that on the server.
Wait, so what is the model here now? How does, I thought it was running on the
In a watch.
on
right?
your watch, yeah.
Right. So there are two trade-off. There are two system design points. Well, one is you can achieve real time by using a simple method. That's just you calculate the centroid of the point cloud. That can be done in real time. And then the other is for you offloading the data to the cloud, and then that will give you an offline result for other purpose. Let's say understand your activity over the day, precise hand activity recognition, but that cannot be done in real time. I think.
Transition probabilities.
I'm sorry.
How do you determine the transition probabilities to begin with for your HMM?
How do you train your HMM?
How do you train your HMM?
Right. So this transition probability actually here, right? So it depends on this noise model basically. And the noise model, we do that by putting the watch on the table, and then we see what is the variance, and from that we generate these parameters. Yeah.
So synthetically. Okay.
Yeah. And then this figure shows the accuracy. X-axis shows the error, and y-axis shows the CDF. And this black line shows the real-time accuracy, which means we just use the centroid, which is not always working, right? And this red line shows what we can do offline using the Hadermark model. I think what you're saying is right. It may not be the best and fastest method, but it gives the, at least in theory, that it can give you the best estimate. It's not in real time yet.
All I was saying was, there's been a bunch of work in the graphics community, in the motion capture world, where they've actually done similar work with accelerometers as well. And the way they solve the scaling problem there is, how in Viterbi you look at all the paths using dynamic programming and you get the n squared.
Mm-hmm.
Instead of using all paths at every point, you can just pick the k most promising paths. It's a standard thing called a beam search. So you focus on that. So then you can do the HMM much faster. So you might want to try that.
Yeah.
It might.
Yeah,
I think that's how
that's a good
to solve a very. So this notion of getting pose estimation from accelerometers has been done in the motion capture community using that, and they use all the similar insights there as well. And you might want to look this up.
But will it speed it up enough to
Yeah.
run it on the watch?
Well, I don't know about the watch, but it's certainly not n squared at that point. So n squared is what you're starting with.
You might be able to ship it to us. Yeah.
He's probably implemented this, right?
We implemented this. So currently, right? Currently, if for 1 minute trace, we take 10 minutes to precise. It's like 10x time.
On the watch or on the server?
On the server. On the server. But suppose you have more computation power, probably can do it better, or you can choose, try to use different beamforming Hadermark model decoding. That could also speed up. But I think in the near future, I don't think this is really possible on a watch for the offline, right? Anyway, yeah. And we have sure.
You say, how did you measure the ground truth here?
Oh, we use Kinect. We use Kinect, yeah. Yeah.
I mean, the main use of Kinect.
I mean, going back to the question about determining transition probabilities, I mean,
Right.
you could put people in front of a Kinect and also have the watch on and have them move and then record data that way.
Right.
Did you guys do that?
So if you do that, then so there are many problems because the acceleration tracking error also depends on watch orientation estimation. So all this mixed together is hard to record a precise watch orientation. So that also have impact on how good is your acceleration, right?
I mean, but at the very least, you can record the elbow position, right?
Yeah, but your watch is on the. First of all, your watch is on wrist, and even if you put it here and try to estimate this, Kinect is not that good yet to give you precise accelerometer level model. Not that good yet, right? It can do.
It would seem like its frame rate is sufficient for that.
But so you can see the acceleration kind of similar, but that model is not good enough because it's not that precise, right? Let's say you have a 2 millimeter, 2 centimeter error, but that will have a large impact on your acceleration estimation. But Kinect cannot give 2 centimeter accuracy today, especially for this kind of tracking.
That's interesting. We found its accuracy to be quite good, sub-centimeter for sure. Anyway, maybe not for the
Maybe you are using the latest Kinect. Right. Yeah.
We're using actually, but that's okay. We can take it off.
Yeah. So, but maybe if that's good, then we can do that too, right? We can build a better model possible, right? Yeah. And we have this demo. So this user is using the smartwatch and then trying to write in the in the air, and then writing ABCD, and this right line shows the Kinect, and then this dot shows what our system tracking result is. So even though here we let the user write A, B, C, D, but in our system we also do free-form gestures and all kinds of evaluations in the paper.
Is this the version that runs on the watch, or is this the one that's 10x?
This is the version runs offline. So this is the offline result.
What would it look like if you ran it on the watch?
We have that video online too, and if you're interested, you can check it. I think I linked that too. We have a side-by-side comparison of real-time, offline, and ground truth. Yeah. And so the offline accuracy here is around 8 to 9 centimeter, and the online, and this online real-time tracking is about 12 to 13 median accuracy. Yeah. And with that, I want to very quickly talk about the last piece of work, which is about hand tracking, hand gestures. I spent only 1 minute about this. So the question here is, can we use the smartwatch to understand what the user is typing on a keyboard? Right? So that will be a security problem or privacy leakage, because we use the smartwatch to track steps or calculate calories. What if the user can use the smartwatch to understand what you're typing? So we have a couple of challenges, right? First of all, as before, right, this noise, the sensor data on the watch are noisy. And secondly, your watch location is not necessarily your finger location. You tap ASDF, your wrist doesn't move at all, right? And third, we don't have the right hand data. We have only one hand watch, right? And then we solve this, and also, of course, we don't have training data. When we attack somebody, this guy won't train the typing for us, right? So we solve these challenges using decision tree, machine learning, karma filtering, and we also borrow the English word structure from dictionary, and we combine these together. And we have detailed result in the paper, but in short, when you type a word longer than 6 characters, our system can, on average, shortlist 10 words that will include the word that you have just typed. For example, if you type confident, and out of 5,000 words in our dictionary, we can rank confident in a second. And so in summary, right, so our devices have this computation and sensing power, and we can use those as a sensing and computing lens for our society. And it's possible by using motion data precisely, we can use this to build interesting inferences on humans. And my research focuses on designing these inferencing techniques, right, using the multimodal sensor data from the mobile devices, and do this location, posture, and gesture estimation. And our research goal, the ultimate goal, is building the system and has impact. And beyond that work, I have talked about, I also work on outdoor localization, context awareness, search, mobile security, and augmented reality. And moving forward, I plan to spend on this human inferencing techniques research for several years, but I will broaden to not only the motion sensor, I will talk about, I will do other research to other sensors, sensing dimensions. And I will do both bottom-up and top-down research. For the bottom-up part, I will not only do this indoor localization of posters, I will also want to understand the finer grain, finger gestures, cross-sourcing, and other behavioral analysis. And I also look at its privacy problem, because as that project has shown that, right, there are privacy challenges, even though the sensing are good, but it's a double-edged sword. They can have privacy concerns. And then at the top down, I will try to leverage this lower level system building blocks to build the system's applications, such as augmented reality, smart home, vehicle analytics, and mobile health applications. With that, I'd like to thank you for your patience, and I'm happy to take any questions and comments. Thank you.
In terms of future directions, what do you think is the single biggest opportunity here in that space that you talked about? You talked about many, many things. What do you think is like a big...
Can you show us your slide?
Sure.
What do you think is the single biggest bet or opportunity that we can make in this space? Because to some extent, things like accelerometers and these low-level sensors, it seems like everybody is doing something or the other, and lots of stuff has already happened. So, what's the biggest possibility in your mind?
I think I will focus on mobile health and physical analytics. That will require many underlying techniques that's still not ready today. And also we have this wearable devices and HoloLens, right? And all these devices together. How can we leverage those together to build detailed, fine-grained inferences?
How do you use HoloLens for mobile health, for example?
So for mobile health, I'm not really sure, but if you have some sensors on your head, I think that could maybe, I'm not fully sure, of course, right? And have never played with that. But I think maybe you can use the sensor data to infer your detailed activity recognition, and you can combine those sensors with your smartwatch and smartwatch and mobile phone together to do something interesting.
Hey, do you think you grayed out indoor localization? Are we done?
Not yet, I think. It's still not there, of course, yeah. And,
okay.
Yeah.
Are you done?
For indoor localization? I think if there are interesting ideas and collaborations, I definitely am open-minded to work on that. But I'm not saying I will have to work on this for a couple of years. I'm not sure. Yeah.
All right.
Thank you so much.